Hello, this is Unit 17, Lesson 4. This is about patterns, and it's also about which are specifically arithmetic and geometric sequences. So we're going to talk about that today. But the thing that we really need to do more than anything else is if you've got any kind of question or think you're going to have any kind of question, get a piece of paper and something to write with, and then that way you'll be ready to take down your question so that you can bring it to class before we start any work on this tomorrow. Okay, so let's go with this and let's see what we got. Okay, definitions. A sequence is a list of numbers or objects in a significant order. So this means that the way that they're put together means something. A sequence can be written as a list of numbers like 1, 4, 7, 10, 13, 16, 19, and so on. Or it can be as a list of objects like this. Notice we have a square, 2 squares, 4 squares, 8 squares, and then 16 squares. Okay, two common kinds of sequences are arithmetic and geometric sequences. An arithmetic sequence has a common difference between consecutive terms. A geometric sequence has a common ratio between consecutive terms. So what this really means is that if it's an arithmetic sequence, it's going to add a particular number to it each time. A geometric sequence, by the difference is that it's going to multiply by a number each time. Okay, the formula for an arithmetic sequence can be given like this. A sub n is equal to a sub 1 plus the difference times n minus 1, where d is the common difference, n is the location in the sequence, a sub 1 is the first value in the sequence, and a sub n is the value of the sequence at location n. Okay, the formula for a geometric sequence looks like this. A sub n is equal to a sub 1 times the ratio raised to the n minus 1 power, where r is the common ratio, n is the location in the sequence, a sub 1 is the first value in the sequence, and a sub n is the value of the sequence at location n. The domain, or the permissible value for n for both an arithmetic and geometric sequences, are the positive integers, 1, 2, 3, and so on. It is important to note that there are many other different kinds of sequences which are neither arithmetic nor geometric. For example, consider the Fibonacci sequence. 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, and so on. You'll notice here outside of the first two terms that there's neither the same difference between any of them or what's going on here, because it's a recursive sequence in which the value of the term is given in terms of the value or values of previous terms. For the Fibonacci sequence, all but the first two terms are the sum of the previous two terms. So after you finish with 0 and 1, then 1 plus 0 is 1, 1 plus 1 is 2, 3 plus 2 is 5, and so on. Okay, example 1, they want us to identify this numerical sequence as arithmetic, geometric, or neither. If it is arithmetic or geometric, they want us to identify the common difference or common ratio. So our sequence here is 1, 4, 7, 10, 13, 16, 19, and so on. Okay, as you can see here, if you add 3 to the previous term each time, you get the next term. So that means that this is an arithmetic sequence because you can add the same number each time. The common difference here is 3. Okay, example 2, they want us to identify this graphical sequence as arithmetic, geometric, or neither. If it is arithmetic or geometric, they want us to identify the common difference or common ratio. Okay, so we have square at the first position, 2 in the next one, 4, 8, and 16, and so on. Okay, so let's see what we got here. So if we take 1 and multiply, or actually what we actually have here is this, okay? We're multiplying by 2 each time. So the common ratio is simply multiplying the number of squares in each term to produce the number of squares in the next term. The common ratio is 2, so that's what we have. Okay, in fact, this is the powers of 2, because if you start with 2 to the 0, go to 2 to the first, and so on and so forth, you will get exactly what the number of squares are each time. Okay, example 3. For each of the following examples, this goes for all of them that follow this, they want us to identify the sequence as arithmetic, geometric, or neither. If it is arithmetic or geometric, they want us to write the general formula for the sequence and then use the formula to find the 10th value of the sequence. Okay, so we have 5, 1, -3, -7, -11, -15. So if we subtract 1 from 5, we get 4. If we subtract 4 from 1, we get -3. If we subtract 4 from -3, we get -7. And 4 from -7 gives us -11. So this is an arithmetic sequence. Common difference is -4. Okay, so a sub 1 is equal to 5, and the difference is equal to -4. So that tells us how to set up our formula based on what we had for our definition earlier. So a sub n is equal to a sub 1 plus n minus 1 times the difference. So fill it in, we get a sub n is equal to 5 plus n minus 1 times -4. Okay, so that's one of the answers. Now we need to find the answer for the 10th position. So we substitute 10 in for n, so a to sub 10 is equal to 5 plus 10 minus 1 times -4. So a sub 10 is equal to 5 plus 9 times -4, which is 5 minus 36, which is -31. So there's our two answers that we need for this question. Okay, example 4, they want to know the number of segments. So the first one has 2, the second one has 4, the next one has 6, and then the final one here has 8, and then it continues. So what this is this is also 2, 4, 6, 8 like I got here. So you can see what's happening is every time they're adding 2, so it's arithmetic, which gives us a difference with a difference of 2. So we put it into our formula that they gave us. A sub 1 is 2, D is equal to 2, so there we are. A sub n, that's our formula, is equal to a sub 1 plus n minus 1 times the difference. So a sub n is equal to 2 plus n minus 1 times 2. Then we need to find the value for a sub 10. So we substitute 10 in for n in our formula that we just developed. So this gives us a sub 10 is equal to 2 plus 9 times 2 is equal to 20. So there's our two answers that we need to satisfy this question. Okay, example 5. We got a list here of 2, 6, 14, 30, 62, and 126. So what we've got here is what? This one is an example of being neither one, because it does not have a common ratio and it does not have a common difference. So this is neither. Okay, example 6, they want to know the number of squares in this one. So here's our sequence. We have 2, 6, then it looks like what we've got is 18, and so on and so forth. Okay, so let's see what we can find here. 2, 6, 18, and 54. So it's geometric because each time they're multiplying by 3, because 2 times 3 gives us 6, 6 times 3 gives us 18, 18 times 3 gives us 54. So a sub 1 is equal to 2, r is equal to 3. So the formula we have says a sub n is equal to a sub 1 times r raised to the n minus 1 power. So our sequence is represented by a sub n is equal to 2 times 3 to the n minus 1. Okay, so we need the value at the 10th one. So a sub 10 is equal to 2 times 3 times 10 to the, or raised to the 10 minus 1. So this gives us 2 times 3 to the 9th, which gives us 39,366. As you can see, some of these geometric sequences get very large or very small very quickly. Okay, example 7 says 90, 30, 10, 10 over 3, 10 over 9, 10 over 27, etc. Okay, notice what's happening here is each time we're dividing the previous term by 3. So a common ratio is going to be 1/3. So once again, we start out with our identification. The first term is 90. The common ratio is 1/3. So we put it into our formula that tells us a sub n is equal to a sub 1 times the ratio raised to the n minus 1 power. So this gives us a sub n is equal to 90 times 1/3 raised to the n minus 1. Okay, now we need to find the value of the 10th term. So the 10th term is going to be represented by a sub 10 is equal to 90 times 1/3 raised to the 10 minus 1. So this is going to be a sub 10 is equal to 90 times 1/3 to the 9th power, which gives us 90 over 19,683, which will reduce. So we go ahead and reduce this, and it gives us 10 over 2,187, or approximately 0.004572. In this case, the preferred answer would be the fraction. Okay. Some other geometric patterns that are not sequences but follow other rules. 2 are very important ones. One is called a tessellation, which is a way to put things together on the plane. You see that quite frequently. One example of that is the way they have the floor tiles and the ceiling tiles in here. Okay, you notice that they fit almost exactly, and if they had been measured correctly, you could have fitted them in exactly all the way across. Or if you extend the plane far enough, you will find out that there will be even numbers of them, or even sections of them all the way. In other words, you wouldn't have to cut one up to make it fit. Okay, the other thing is a fractal. Fractals are very important. It's probably the most recent discovery that has come about, but what it comes down to is it's a consistent repetition of a value of a function. So when you get that, what it comes down to is this has lots of uses in terms of studying how actually things in the world actually work, because this thing will let you simulate coastlines very closely. All right. We're not going to go into those, but what I'm saying is if you ever come across those terms, you need to investigate and see what's going on with them. All right. Thank you very much. If you've got any questions about any of these, be sure you bring them to class and we ask us about it, and then we will be glad to explain them to you before you start your work. Thank you very much. Goodbye.